2.2, density curves and normal distributions. We're going to go up into the activity. Then I'm going to have you do the first part of the activity on your own before class, and that's where we're going to stop. Okay, so the first definition here, what is a density curve? Okay, so there's only two components that have to be met to be a density curve. The first one, it's always on or above the horizontal axis, and that's just the x-axis for our purposes, right? The reason I call it horizontal, it's just a more general term. Like, in case you're talking about time as the x-axis, I call it a different variable. But for us, that's just the x-axis. So it's always on or above the x-axis. And the other piece that has to be for the curve, it always has an area of exactly 1 underneath it. So two things. It's either on or above the x-axis and has area exactly 1 underneath it. So I'm going to draw the simplest one I can think of. Let's see up top here. I'm going to draw some axes. The x-axis will be down there on the horizontal. Okay, so and then I'm just going to draw a rectangle there. And I don't know what the values are, but we'll go from 0 to 1. So if you think about it, the question is, what is the height of this rectangle if the area is exactly 1? Because the first component's met. The first component is always on or above the horizontal axis. Well, you can see my red lines here. That's on or above the axis. So the only other thing I need to do is be area 1. So actually, the height would be 0.5, and then that would give me an area of 1. So that's the simplest density curve I can think of. The easiest one to draw has area 1. It's above the x-axis. Okay, so the next part there. A density curve describes the overall pattern of a distribution. The overall pattern is what it describes. The area underneath the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Okay, so it probably doesn't mean a whole lot to you right now, but we'll get to that. That's just the formal definition. Okay, so you can think about these density curves as just something you draw over a dot plot or a histogram. So we could have built this histogram off a bunch of dots, right? So whether it's a dot plot or a histogram, we're just going to try to fit a smooth curve over this that represents it. So go ahead and try to fit a smooth curve over this thing. So let's see what I come up with here. Fit a smooth curve that estimates this pretty well. So that's my estimation. I know, like, I got a little bit above, I know that. I'm a little bit outside, but in general, if you could just draw a curve over it that fits it. In fact, if you drew something that looked like this, I'd be okay with that. That's pretty good too. In fact, I like that one better, so we're going to keep that one. Oh yeah, that's kind of nice. So, how do you describe a density curve? Okay, so the median, we've talked about this before. The median is the equal areas point, or the point that divides the area under the curve in half. I know we've gone over that before. So if you could paint half the curve one color and paint half the curve another color, right there in the median, in the middle, that would be the median. The mean is the balance point. So I want to talk some more about that. What does it mean to be the balance point for the distribution? Okay, so the median and the mean are the same only for a symmetric density curve. If it's symmetric, they're balanced together. Mean and median, they're the same. But if it's skewed, that's when it'll be a little bit different, because that skew pulls the mean to the right or to the left. So if you think about this first curve here, 50% on the left, if I could just paint that, that's 50% of the area, right? So this stuff over here, 50%, and then on the right, obviously, since it's symmetric, that's also 50%. Okay, so the median, right there in the middle, it's also the mean. Because if you think about this, if you try to hold this curve up, like see I'm holding my fingertip right now, it would balance right there on my fingertip. It wouldn't fall right or fall left, right? It would bounce right there. So if it's symmetric, it bounces right in the middle. The mean and median are at the same point, because the median that's the equal areas. Okay. But what about if it's skewed right? So you see the median is still here. So that's actually still equal areas. And I'll draw it here again too. So 50% of the area in purple, that's on the left still. And then, so here's the median. So if you look to the right of the median, that's actually representing the other 50% of the data. So the equal areas point even though it maybe looks like I'd use more ink on one or the other, but it actually is the same. So that's equal area. But for the mean, because it's right skewed, it gets pulled out, right? These larger values pull it out. And you can remember, you can think about this as like a dot plot underneath here, or a histogram underneath here. So it's getting pulled out by some outliers. So let me just, let's get that mean back out. So the mean's right here, because it wouldn't balance if I tried to hold it here. It would fall over this way to the right. But it would actually balance right here where the mean is. If I held this distribution up on my fingertip here, the mean would actually balance there. Okay, a couple more key points to note. A density curve is an idealized description of a distribution. That word idealized there. So notice before we just fit a smooth curve over it. So even though it's not perfect, right, we just kind of approximate it to fit kind of a smooth curve, whether it's a nice dot plot or a histogram. That's why it's like an idealized in a perfect world. We would use that nice smooth curve. So we distinguish between the mean and the standard deviation of the density curve, and the mean and the standard deviation computed from actual observations. So before for samples, for like mean and standard deviation, this was our notation for mean and standard deviation. So those actually come from samples or experiments that we conduct. When we talk about normal curves, which we're getting ready to talk about, we're going to use a different notation for mean and sigma, and we'll use these throughout the course, throughout the semester. They're Greek letters. You may have seen them before, actually. So for mean, that's the Greek letter mu. It looks like a U with a little tail over here on the left. Greek letter mu. And for standard deviation, that's the Greek letter sigma. It looks like a little O with a tail on top. So these are like perfect world values. These are ideal world. If a normal distribution works, we use the true mean and the true standard deviation, we say. And this, we use these when we're talking about values we get from our own samples, our own experiments. Okay. So let's talk about normal distributions. You might have heard the word before. If you're in AP Psych, maybe they've said it there. Normal, 3 characteristics. It's symmetric. Not only is it symmetric, it's single-peaked. So you already know it's not bimodal, it's unimodal. And it's bell-shaped. So it's symmetric with one peak, and it's bell-shaped. So we're pretty much talking about these types of curves right here. And any normal curve is completely described, that's what this next blank says, completely described by giving its mean mu and standard deviation sigma. So all you need to tell me about a normal curve, it was what the mean and standard deviation are. I really don't need to know anything else because I already know it's going to look like one of these two curves. It's bell-shaped. So just give me the mean and the standard deviation and we're all good. So even though one of these is like short and stout and one is tall and skinny, they're both normal. So you can see they're both symmetric, bell-shaped, single-peaked. One actually just has a lot bigger standard deviation. So this one, what that's trying to communicate, here's the mean in the middle, has a bigger standard deviation, which makes it wider and not as tall. Whereas this one, it doesn't have as big a standard deviation, so it's not as spread out. So it's more stacked up in the middle, it's taller and skinnier. But they're still both normal distributions. So as long as I know the distribution is normal, the only two values you need to tell me about are the mean and the standard deviation. I don't need to know about anything else, just those two things. Those are the only things that really concern a normal distribution as far as how you describe it. Okay. And then the definition down there at the bottom for the normal density curve. First thing you should know, and you could probably tell by looking at the graph, is the mean will be at the center, right? The center, because it's symmetric. So just like both of these graphs here, the mean's smack dab in the middle, which means the median, by the way, would probably also be smack dab in the middle. The standard deviation. The standard deviation is the distance from the center to the change of curvature points on either side. What do I mean by that? The change of curvature points. Okay, so let's look at these two graphs. So the standard deviation for this one on the left here, it's this distance. So if I compare this standard deviation to the mean, that point right there on the curve is special. This point is special. So if you can see it and look closely at your notes, this is called the change of curvature because this is like, let's think about like a ski slope, right? This is where the slope stops going down so much and starts going out. Or another way to think about this. Okay, up here, at the top of the curve, this will be like our frowny face, right? That's a frowny face on top of the curve, okay? And the change of curvature point, you could probably guess, is when does it start to turn into a happy face? You got me on that? So I can kind of just estimate where the standard deviation is if I can look closely and see when does it stop bending down in a frowny face and start bending up and out into a happy face. That's the change of curvature point. So let's see if I can draw down this other graph too here. So from the standard deviation to the mean, this one's a lot harder to see because it's tall and skinny, but change of curvature point, when does it stop making the frowny face upside down and start making the happy face? That one's harder to tell because it's balanced right in the middle there. But that's how we can estimate where the standard deviation's at. It comes at that first change of curvature point here. Okay, and then the last little bit here. We abbreviate normal distribution. You'll see this throughout the course. We abbreviate, give me the other, there we go. We abbreviate the normal distribution with mean mu and standard deviation sigma, just like this. So if a distribution is normal, you can call it capital N, and then parentheses, you just write the mean and the standard deviation, wherever they are. So mu comma sigma. That's how you can describe normal distributions. Give me that green hand back. I like the green hand. There we go. Okay, so the last piece on this page. Why do we care so much about normal distributions? Oh, give me the back. Give me the back. There we go. First of all, they're great approximations or great predictors, describers of real data. So, like height, weight. If you look at the population, IQ, test scores, a lot of things become normally distributed. Okay, and then if you graphed their dot plots or histograms, you could draw that smooth curve over it and you could approximate it to be normal, like one of these guys. So it also describes a lot of chance outcomes. Okay, so this is where I'm going to leave you. I want you to jump in and try this first part of the activity on your own. It says, for each of the approximately normal distributions below, calculate the percentage of values within 1 standard deviation of the mean, 2 standard deviations of the mean, and 3 standard deviations of the mean. The first one, there's a dot plot showing the weights in grams of 36 Oreo cookies. The mean of this distribution is 11.392 grams, and the standard deviation is 0.081 grams. Wow, that really just made me hungry for Oreos, and I really wish I had an Oreo picture put like right here, right now. Sorry. So to get you started, the mean is 11.392 grams. This thing. So let's trace that over here. So 11.392. I think it would be, use dots, right here, about right there. So this could be our mean. So if you're going to look 1 standard deviation to the left or right, like this guy, the mean plus or minus 1 standard deviation. So 11.392 is the mean. 11.392. And if we look to the right, 1 standard deviation, all you have to do is add whatever the standard deviation is. 0.081 grams. So standard deviation is 0.081 grams. And this should give you a value. And then let's do the same thing. Go into the left, because it says plus or minus 1 standard deviation. So let's look to the left. Subtract 0.081 grams. And then that should give you a value on the left-hand side. So when you come up with those, put those here. And then do the same thing for if you added 2 standard deviations. So instead of 0.081, look at the mean and add 2 times 0.081 and see what you get. And then for each one of these, between 1, 2, and 3 standard deviations, hopefully you know what plus minus means, right? That means look to the right, look to the left, what's contained in that. For each one of these, say what the percent of observations is within that. So let's just say, for example, I look 0.081 this way to the right, and I catch all these values, and I catch all these values. So what would the proportion of values be in there? Well, there's 36 cookies. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So the percent, I would say I've got 25 out of 36 in there, whatever that percent is. Okay, so your task is just to come up with the first part here, and then we'll pick this up tomorrow in class. That's it for the notes. See you tomorrow.